All right. We're going to go ahead and get started here. It's 11:10, and when I did my practice run of this, I was 5 minutes over, so giving myself all the time in the world. All right, so my name is Greg Bilodeau. I'm just going to sit from here the whole time. I am a mentor for 930. I've been with the team since 2007, where I was a student, one of you guys, for 4 years. I put a funny comment. That was like 4 control systems ago, soon to be 5. I am First Wisconsin FRC program manager, so I talk to a lot of your mentors these days. And I'm a senior Android developer at Geico as well, so I sit in Java all day long. As much as I want them to use Kotlin, the app is 20 years old, and so it uses Java. Yeah, we're going to jump right in. So there's a few slides I'm realizing now that I meant to edit and I didn't, so we're just going to have things like this next slide, just going to have a grayed out word for no reason. But yeah, so today we're going to talk about programming without a robot. So obviously during the season, you guys have to wait for your teams to build, to design, to fabricate, and assemble their robots before you can really test things. And there's like 4 big steps to programming a robot in general. More than 4 certainly, but I'm only going to focus on 4. There's hardware configuration, which means like, setting all your CAN IDs, making sure everything's talking to the robot properly, making sure you got your encoders recording in the correct units. I know back in the day it used to be like encoder ticks per 10 milliseconds or something ridiculous that you had to convert to rotations per second or something. There's writing a bunch of business logic, so writing all of your subsystem classes and your commands to interface with that hardware, to tell your Kraken motor to spin at 8 volts until it reaches a position and then stop spinning, and to hold it. We're going to call that business logic today. There's control loop tuning, so you've got your arm, and you want it to go up here, and you want it to hold here and resist gravity, right? And you got to also overcome all the friction of your robot. Maybe you had a freshman that put it to get the gearbox together, and he over-tightened everything. Always happens. Overcoming all of that with your control loop tuning, and then stringing it all together. So like all of the things before were just like the bare minimum to make it work. The next part, which we're going to call like the application logic, is the fun part. It's where you like make it move up while your intake goes out and aims while you're driving, or you use your camera to see the goal and it aims right where you want to do. All of the stuff where you're applying the business logic that you wrote before. And so I'm just going to like skip between these slides because I don't remember my intention here. What parts require a robot now? So obviously you can't be setting CAN IDs without a robot in front of you, without a motor plugged into your laptop to do the CAN ID. You can't verify that your encoders are spinning the correct direction and incrementing the correct direction. And you can't do control loop tuning without that robot right next to you, right? You're not going to be able, you can estimate the guess. And we're going to talk a little bit about that today. But in the end, everything that we're going to do today, these 2 things you're going to have to either do or redo. And that's going to be a little like weird part of this, is there is going to be code you're going to write that once you have the robot is not going to be used while it's on that field. It still can be used when your programmers are like over in their programming room while the mechanical team is fixing the robot because you guys drove it into a wall in autonomous. Happens every year. Where you can still use this. But these are the 2 things that require a robot. The parts that we're going to talk about today are like the business logic. So writing those subsystem classes, writing the commands that use them, and that application logic of stringing it all together. You can do, you can structure out your autonomous modes entirely without a robot. Obviously, the tuning is what actually makes it work, and you can't do that in simulation. But you can make sure that, for example, if you have an arm that goes out and an intake that goes out, and if they go out at the same time, they're going to hit each other, you can make sure that you've got your code strung together such that the arm moves first, and once it reaches a certain point, then the intake moves. All of those commands you can string together in simulation first. And then once you get the real robot and you tune those individual control loops, a lot of it might just end up just working from there on. There's going to be hiccups, but the idea is to get as much work done before you've been handed that robot and how you can do it. So that's what we're doing today. I've got this funny thingy, this funny chart that I tried to make that the black on teal is probably hard to read for you guys, but this is how we used to write subsystems and how a lot of teams still write subsystems, where you have all of these different things entangled into one single class. You have all of your Krakens, all of your CAN coders, all of your Neos, how you're configuring them, like right at the top. And then you have like the periodic method where you're like, okay, I have a set point, I'm going to feed that into my Kraken right now, and I'm going to grab a feed forward from my encoder, feed that into there. You've got the commands, which change all of that to say, I want my set point here, or I want to wait till my arm is past 45 degrees. And then if you're better than we were a few years back, you also have some simulation logic in there to try to string it all together. It gets really difficult to do when you're relying on hardware that is not there on your laptop. You do not have a Kraken plugged into your laptop. Now, CTRE and Rev are starting to kind of put some simulation stuff into their APIs that you can utilize. We utilized them last year. If you go look at a couple of teams, you'll find them using the architecture I'm going to talk about with some of the CTRE built-in simulation stuff that kind of muddles this a little bit, but we're going to talk about kind of a more pure method here. So what we're going to do today is to break that big monolith into 4 distinct sections. And we'll start on the left side. So you're going to build a subsystem class that extends that subsystem base and really just has some commands in it that say, move my set point here. You're going to have this next in the middle, this I/O layer, input-output definition layer, which is going to manage your logging. So the most useful thing you can do during control loop tuning is log everything as possible so you can reference it as data while you're tuning. And it's going to kind of define a contract for how you talk to either hardware on the top there or your simulation on the bottom there. So I've got the 2 on the right there. You then have 2 classes that basically you use one when you're on the real robot and you use one when you're on a simulation, and you can use like the robot.isReal method in there to kind of distinguish between them. But the hardware one on the top is all of your hardware related stuff. Your Krakens, configuring them, setting your inversion, etc., and how it runs those business logic contract. And we'll talk directly about this. And then you have the simulation variant of it, which is the same methods but different implementations that use simulation objects built into WPILib. This idea is called separation of concerns. As you go up into your programming careers, you'll start getting that a lot. You can go really crazy with it, and it's not always great to go crazy with it. But it's good to separate the responsibilities into these different classes so you have smaller classes that are easier to debug and easier to maintain, okay? And I already talked about this application business hardware layer. This may not be the exact right way of using those terms, but it's the best way I could break it out for how we do it in robotics. So the rest of this is going to be, I'm going to be coding up here and playing around. I've got my Xbox controller somewhere. Oh, there it is. That we'll be having some fun with. And yeah, so let's close this out, and I will open this up. Let me get my sample one here. So what we are starting with today is I've got a project already begun that has a couple basic things. And the most substantial one is I went to CTRE's GitHub, and they have their Phoenix 6 examples, and they have a project in here called Swerve with Path Planner. This is basically what is output by the SwerveLib generator that you use. The only problem with the SwerveLib generator is you have to plug into a robot to do it, and we are not going to have a robot at the time here, okay, to generate that project. So I cloned this, brought it down, and basically just put it into a core project. So you'll see here like this command swerve drivetrain that it makes. It makes for you, just bing, bang, boom, done. And I'm going to real quick, like we're just going to hit simulate right now. And I'm going to turn on my Xbox controller. And so this is the simulation driver station basic tool. What I'm going to be using today and what you guys should always be using is Advantage Scope. Another tidbit here, I'm using the 2025 versions of everything. So this is 2025 WPILib, 2025 Advantage Scope. I'm going to connect to my simulator, and you see all these fields here. By using that Swerve with Path Planner project, which I imported about an hour ago sitting over here, I take this robot pose. Technically, it's already in here. I'm going to delete it. I take this robot pose. I drag it in here. You might see in the bottom left a robot appears. I hit enable, and oh, I got to drag my... This is going to be the worst part is, oh, it's already here. Maybe if it'll stay here. When I was doing my demo, I had to drag this Xbox controller every time I opened this, and I wanted to die. And I just go forward. And so you'll notice one thing here. I imported one of our robots into Advantage Scope. You can do that. You can export your CAD file and import it in here to do some 3D stuff. But I'm just driving with my stuff. That just comes built in with CTRE stuff. I think Yagzel has a very similar thing. So just giving you an idea of what I am starting with here. I'm going to close this because it will kill my system eventually. I've also added Advantage Scope, or Advantage Kit clearly, and I added one file here from Mechanical Advantage, the makers of Advantage Scope, called logged tunable number, and it basically just outputs a double to the smart dashboard that you can change, and it'll read it back in the same code loop, so you don't have to like restart and recompile every single time. That way when you're tuning control loops, you can just test it, say, that's not quite right, change it in network tables, and you don't have to redeploy. Those are what I'm starting with, okay? So today we are going to, we're going to code like 75% of the simulation for our 2023 robot. I picked that one instead of our 2024 one because it has an elevator and an arm, okay? So two different things. We're not going to do the wrist, so it's going to look a little funky in the simulation because it's not going to have any way to pick up game pieces, but we're going to have here. So we're going to start. The very first thing I'm going to do is I'm going to make a quick class here called robot state that it is just going to hold the position of our elevator and the current position of our arm. Today I'm going to be using the new Java Units APIs. So coding, it's been there in 2024 where you can code in like inches and meters. They made it a lot nicer this year. So what I have here is what's called a distance. It's a mutable distance, which means I can change it instead of immutable. And I'm going to try to spell things right. So we have elevator position, and we're going to have a mutable angle called arm position. I'm going to quick make this a singleton class. So I'm not going to talk too much about like the specifics of just coding in Java. All right, so like I might talk a little bit about like, okay, I'm going to make this a singleton class, which means there's only going to be one of these in the file. The other stupid thing. So this units class that they're going doesn't import correctly. So like you see inches has a red line here, and it just wants me to create a class. There is a static import that I'm going to have to copy paste into every file that does this. And then import mutable angle 0. So you see how it says inches here. This way, the biggest problems I always find with control loops and tuning is units. You are making assumptions that you're setting your positions in meters, but you're reading from your encoder in inches, and everything is just a double. So it's kind of unclear until you actually log things. This new Java Units API is very, I misspelled position, explicit about what the units are, and you can then turn them into doubles, but you can convert them and etc. So I'm going to work today in inches and degrees. Some things are going to return radians, and I will convert those into degrees. Some things are going to be meters, etc. So we're just going to real quick make a couple helper methods for updating these files. And it's going to be like elevator position equals, nope. I have the GitHub Copilot thing installed, and so it's going to try to make suggestions for me, and sometimes I'm going to take them. Like that one's good, and sometimes it's just going to be wrong. But update arm position, and that's going to be a mute. Oh, look at that. It figured it out. So we're just having two methods here that update the arm position and elevator position, and I think that's all I'm going to need for now. Okay, so that was kind of a boring part. Let's actually get into this. So I have this subsystems directory here. which we are going to start with the elevator. I'm going to make 4 classes. I'm going to make an elevator. This is going to be our subsystem class. Remember, we had 4 boxes there. I'm going to make an elevator IO. I'm going to make a elevator IO sim. And technically, you would also have the elevator IO hardware here. So you could be like elevator IO Kraken if you use Krakens. We're not going to really go into the hardware aspects of this. This is going to be code that you've already written on your robot. I'll put it in here just so it's clear. And then I'm going to have one more that I didn't talk about. I'm going to make an elevator visualizer class. And this will be how we put stuff on the dashboard that like moves and does cool things so we can visually see what's happening. So we are going to start actually in the middle, and we're going to start at this IO layer. So what I said before is this kind of defines a contract that our hardware and our simulator adhere to for how to talk to those 2 things. It's going to have a couple methods to start with. It's going to be like, okay, what are some of the things that our elevator needs to be able to do? It needs to be able to take a voltage and send it into whatever you're using, your Krakens or your simulation. Okay, whoops. There we go. It's also going to want to run to a set point. So remember, we're talking in units here. We were talking inches. We can just use a generic called distance, which can be inches, meters, feet, anything, millimeters, I think, as well. And we're going to do one more method for now, and we're going to do a stop that takes nothing. Okay? So these 3 methods we would have to implement in our hardware and our simulator to run our robot. So let's go look at the simulator first, or at all. So the unique thing, or the objects that WPILib provides for simulation is, for an elevator, there is an elevator sim class. Okay? This, you basically define your, and unfortunately it is not a nice constructor here. You define the physical properties of your elevator, how much it weighs, what's your maximum height, what's your minimum height, how many motors are powering it, what the gear ratio is to those motors, and one other thing here. Then it runs a physics simulation on it for you. So the first thing you need to pass in here is your motors, and so there's this helper class called DC motor, which I'm going to say get Kraken, and it's going to say basically this is going to be run on 1 Kraken motor. The next thing is your gear ratio. A lot of things today I'm going to just be putting as like hard-coded values. When you have more time to do this, I would suggest a constants file that defines what these are with very readable variables. Okay, so like I'm putting a 4 here. 4 means nothing, right? 4 is a number. I would put that in a file called gearbox. And I'll do that for the arm, but for speed here, we're going to do here. The next thing is the weight. So here's where the units really is fun. So like we weighed this, and in America, we use pounds, okay? But in the simulator, it uses kilograms. And so here's a part where I have to, again, go up here and grab this silly import statement and put it in here. So we say it's 9.8 pounds in kilograms. And that converts it for us. And it makes it so that we're using units we're aware of, but we can change it to what it wants. I believe, yep. So this next part, when you're building an elevator physically, usually they're like driven by like a steel cable that goes up and down and runs around, or a pulley that runs, or a belt that runs around a pulley. This thing here is the radius of that pulley or that drum. So it knows like, okay, if it's a 4-inch pulley, is it a 1-inch pulley, etc. So it knows how far one rotation will move that elevator up and down. Then you put the minimum height. So I'm just going to say 0 inches. Again, these are better in constants, but for this one, I didn't do it. You put your maximum height, so I'm going to say 52 inches is the maximum height. I forget what it actually is on that robot, but 52 is a great number. The next thing, which is the real power of this simulator, is do you want to simulate gravity? Okay, it'll be like, do you want gravity to pull down on your elevator when you're not fighting it? And we want that because that gives us a better idea. And technically, you don't need it when you're doing it here, but I think it gives you a better idea of how things are actually going to behave. And then finally, you want the position it's going to start in. So this is just going to be 0. All right, so we have this elevator sim now that when we send it voltages, it will do stuff behind the scenes. So we need to implement that contract. It's going to say that you need to add these methods. So we need to write these 3 methods. We're going to start with volts. This one's real fun. And by fun, I mean easy. Sim.set input voltage volts.in volts. Hooray. We've told our motor to go whatever volts. It's done. We'll do a couple more lines here in a minute. But then in the stopping is just run volts, volts.0. Hooray, we've commanded 0 volts here. The set point's the more fun one, okay? So there are 2 big ways that people do PID loops, right? A lot of times the motor controllers these days can just do them right inside. You would just set PID on your configuration for your Kraken or for your Spark Max, and then you send it set points right here. So you would just say like Kraken.setPoint, whatever, and you're done. Simulation doesn't have that. And so we are going to, this is one of the pieces of code that you're going to have to write here that you wouldn't have to write for the real thing. We are just going to set up a real basic PID controller, okay, using the WPI lib classes. So it's going to just be like private final PID controller. Controller equals new PID controller. And again, I'm just going to put zeros in here. These I would put into constants. And I, like foreshadowing, I talked about that tunable number file I imported here. This is what we would use it for and what we will on the ARM. So in a set point, we get a position. There are just like a couple things, how a PID controller works. So first thing is we are going to get the current position that we are at right now. So sim.get position meters. We need to convert this into a distance, and you'll see it's in meters. So we can say meters.of this. And if we want this in inches later, we can just put it in inches. But again, having your units be explicitly clear helps make more readable code and more debuggable code because it's always the units every single time. And then I think, yep, okay. So then we just need to say, and I like to, again, put this in units. You don't have to. We are going to put that into the PID controller. The PID controller takes your current measurement and where you want to be. So we're going to say position.in, and you can keep it consistent. I'm going to do this one as in inches because that's how we're going to use it everywhere else. And that means I then do the current height.in inches. This line here is where all the errors in the world are always with control loop because implicitly sometimes it's actually in meters, but because they're just doubles that you're passing in, nobody knows. That's why I love how they've done this new units library. You'll see a big error because they haven't converted the whole world to units yet, unfortunately, including the PID. So we just need to say volts.of. Cool, so now we have a voltage, a PID-based voltage that we can use. And we're just going to run volts. You could have a feed forward in here. Feed forwards are great. You would put it right in here as well. We'll do that for the ARM. We're not going to do it for the elevator. Okay, we've written these 3 classes. So technically now, we have the simulation set up to run stuff. Let's quickly go do the subsystem, and I'll show you how we end up using these different classes here. So every subsystem extends subsystem base. And we are going to take an instance of an elevator IO. And that is going to come in via our constructor. Perfect. And we're going to set up a couple other things. No, we aren't. No, we don't need that right now. We're going to do the periodic method that comes with the subsystem base. This runs every 20 milliseconds. And in here, we are, oh yeah, we do need this actually. Private distance set point equals inches mutable 0. So we need the initial set point because the way we're going to end up doing this, and again, I need this silly import. I really should have just made like a snippet just for that import. There we go. So in here, we are going to say this.io.run set point, and we can then make a quick command that says set position. Wow, it already was doing it for us. Almost. The basic, or the functional subsystem APIs here. So just run once and say this.setPoint equals setPoint. And import this. And so now we could hook this command up to a button on this controller and it would try to run that sim. Now, a problem that we're going to have to overcome here, first off, is we haven't logged anything yet. How are we going to visualize anything here on this sim? How are we going to tune anything on this sim? So I talked about it before. The tuning kind of comes in this I/O layer, or the logging comes in on this I/O layer. So we are going to make a container object called elevator I/O inputs. And this is just going to be a series of variables that represent all the things that are going to come out of our hardware or of our simulation. So things like distance, so like our current position on there. Things like, I haven't done this one yet, linear velocity. So again, it's basically, you can see it's already telling us what to do actually. Inches per second. Give me this silly import. There it is again. And what are some other things we want? Let's see. We probably want, so, oh, yes. Oh yeah, you're right. Public mutable voltage applied volts. And this will just be volts for now, mutable 0. We'll import that. And I'm going to put in a few others. So now I'm going to put in a bunch here that the simulation is not actually going to use because it doesn't see it in sim, but you would use it on the hardware layer. So very popular these days is looking at your supply and your torque current and making sure that they are staying, like if you're tuning current limits, looking at these to see, you know, how close are you actually getting. And technically the sim doesn't separate these, but CTRE and Thrifty, now their motor controller, has separate supply and torque current. I think Neos have the same thing, just a little bit different. And then I think we're just going to stick with that right now. So we need a way to update these so that we can log them. So we're going to add one more method here, void update inputs, where we're going to pass in an inputs object, and then we can edit it. This is the only thing about this architecture that I'm not a huge fan of, is the fact that we are passing in an object and mutating it and not passing it back. That's a little dangerous in that, like, you can't exactly keep track of if a freshman accidentally changes this in a weird place. This is the only thing I'm not a huge fan of, but we can, because it's kind of isolated here, hopefully you don't run into that issue. So for the sim, we add that method. It ends up down here. I'm going to quick come over here and just like grab all these things so we can remember what we need to change and just say, oh man, zooming in so much, I'm missing all of my lines, but that's okay. So one quirk with the simulation is it doesn't do anything with time unless you tell it to. So you need to tell it how much time it's progressed since the last time that you read these values. So there's a sim.update where you say 20 milliseconds has passed. Please push the physics simulation forward 20 milliseconds. And then in here, we're just going to be like inputs. And so we're just going to update all of these. So dot position, and it's actually doing some of that for me. Did it do it right? Look at that. Oh, I don't necessarily like that way though. There we go. And we're just going to update each of these. So inputs dot velocity. There we go. Get velocity meters per second. It's in meters per second. Great. So applied volts. This is a fun one. And you saw GitHub Copilot trying to guess here. There is no get volts on the sim. You have to store that, unfortunately. So we're going to go up here, and we are going to say private final mut voltage applied volts equals volts.mutable 0. But because of the way we wrote this, where we have everything kind of funneling through this run volts method, we can just say applied volts dot mutate replace. Yep, volts. So I haven't talked about it a little bit. The reason that there's this mutate version of all of these is because the developers for WPILib were a little scared of how many objects you would be creating using the units library in relation to the garbage collector, because that's Java's biggest failing, is it has this garbage collector that runs indeterminately, and at some point will just like freeze your code for like 60 milliseconds. So they created these mutable objects so that you're not creating a new object every single time, you're just replacing the value inside. So it uses this mut replace. So then down here, and actually I need to go back up there in a second and change one more thing. One thing you guys probably, if you have written this kind of method here before, realize that I missed, is that I'm not clamping the voltage right now. I'm not saying it's going to be negative or positive 12 volts. Your PID controller could send you a 30 volt command. The real robot is not going to be able to send 30 volts. It's only going to be able to send, it might be like 12.5 or something. We are going to clamp this to 12. This is kind of the most awkward part of the units library, is that they don't have a clamp method built yet. So I have to be like volts.in volts, negative 12, 12, clamp it, and then take this, put it in here, say it's volts, and then we're going to pass in applied volts instead, I think. Oh, duh. The effort, yep, thank you. That's not one of the methods I wrote. Okay, so now we've got this. So now, okay, we have done this. Let's quick grab the current. And like I said, the simulation doesn't have separate supply and torque, so we're just going to do it the same as both. But when you have your hardware, this will be different. You can also do things like temperature, and if you go look at other teams that have done this, like 6328 is who I'm basing this one off of, but a lot of teams have started to do this architecture. 254 is another one. They will have one of these objects is motor connected, and it'll just query all the signals that it's using to get these values and say, like, am I getting actually values from this? And if not, your motor's not connected, and then maybe you pop up something on your screen, or, you know, like, hey, your encoder is not working. Maybe you shouldn't let them start the match, kind of stuff. Okay, so now we have this. We need to use it in our simulation, and we have this wonderful periodic method that already runs every 20 milliseconds. So we can just say this.io.update inputs, and we need to pass in a value. So we are going to inputs. Perfect. We're going to pass this in here. Now again, we haven't logged anything yet. There is one helper bit that comes with the Advantage kit that is just what's called an annotation, called autolog here, because the logger from this one really only has like individual values here. You say record output and you pass in some string, some double, or some, like there's this one here that might work. Let's see if it does. Inputs. Nope, doesn't like this one. Oh, because it's expecting it to be byte array maybe. But because we did this function right here, annotations can make compiled classes for you. So it now just made a new class for us that just is appending auto logged on there. And we can say logger.process inputs, elevator inputs. This auto logged annotation kind of gives you superpowers. I'm not going to use them today, but this is the key right here. When they talk about log replay for Advantage Scope, this one method, you can take a log file from a match that you ran and feed it back into your simulation. So it'll use your simulation. It'll run your code, but use the inputs that we logged during that match and just run your code again with those. So you can debug and see how things actually happened. This single line gives you that superpower. We're not going to talk about it any more than that today, but that's the cool. Okay. So that was there before. Yep. That was there before. And the last thing I'm going to do that I forgot to do way back here is I made this private, but I never actually implemented like the rest of the singleton bit. So we are just going to quickly do, and I'm going to do this the lazy way. I'm just going to say private static robot state instance equals new robot state. I'm not going to put any lazy instantiation here and just actually, let's just make this public. That'll make that easy. Again, I necessarily wouldn't do this, but this is also a really low-key kind of class, so it's not the worst. And then, so in here, because we have these inputs, I'm going to say robot state dot and I'm just going to update the elevator position with the inputs that I grabbed from this update inputs method. Okay. I think this will run as soon as we add it to the robot container. So robot container here, there's a lot of stuff. This is all, again, pre-generated by the CTRE swerve lib generator. So everything in here is doing that driving. So I'm just going to like add in something here. Private final elevator, and we're just going to say this dot elevator equals new elevator. And so that's not going to compile because our elevator needs a IO object. So here's where I said earlier, like you can do robot.isReal, and if it's real, you would do like new elevator IO Kraken kind of thing, and then we would do new elevator IO sim. This isn't going to work because I never, oh here. Let's do it and see. Doing this on the fly. So if this doesn't work, I'm just going to delete it. Get my imports. Okay, come on. Import all, please. Thank you. And so then over here, it should just work. So now, if the robot's real, it will use this class. If it's not, it'll use this sim. Let me save all of these off. And let's go ahead and see first if it builds. That'll be really cool if it does. Hey, look at that. Okay. So we're going to start Advantage Scope. Again, the 2025 version. It's connected. So when I go here in Advantage Kit, you'll notice, and I'm sorry, I don't know if I can actually zoom in. Oh, look at that, I can. It's going really slow. I think I just froze it, but I have this elevator now, which has a bunch of values. If I go ahead and enable, nothing's going to happen because I never hooked up a button, but also because we never set our PID values. Our PID values are all 0, which means no matter what we do, it's just going to send 0. So I'm going to really quickly just grab, I'm not going to show tuning of a PID controller in here in the elevator. Okay, doing great on time. I'm going to go into my elevator IO sim, and I previously, when I was doing this, had found that a p-value of 0.3 volts per inch. KP has units, and you can define it in units, like I could actually do. Private final, this object called per, and it's voltage, unit, distance, unit, KP equals volts dot of 0.3 dot divide inches dot of 1. And I could do that, and that, I think this is the only area where the units library fails, is right here. This is way too explicit, or way too verbose, and it really only works for KP. Does anyone know what the units for KI are? Because I've looked and I don't know either. KD is this, but instead of distance, it's like velocity units or something. It's just volts per velocity, per whatever unit of velocity. Yes, but because of the way it's calculated. So like KI is an integral thing, right? It's like a buildup of error. So it's like volts per units of error every 10 milliseconds or something crazy, and KD is volts per unit of velocity, and KP is volts per units of position. I'm just going to use 0.3 here because, honestly, almost every control loop you do, for the PID controller at least, you really only need P. We're going to use a feed forward in the ARM. So I'm going to do that, and then I'm going to add a button. So we're going to just throw it right at the bottom here. We're just going to say joystick dot, I like Y because it's the top, dot while true. We're going to say elevator dot set point, and we're going to go to inches dot of, we're going to go 50 inches, 50 please. And what did I do? Oh. This should probably not be mutable. Set point dot. Thank you. Whoopsie. That's the problem when you let GitHub Copilot do its thing sometimes. And I'm going to do this on a new line. So while I hold down the Y button, this is going to set the set point to 50. And I'm going to then say on false, elevator.setPoint 0. So when I release the button, it's going to go back to 0. So let's give it a shot. There we go. There's the errors I was hoping for. And by hoping, I mean kind of expecting. Why does it say this is null? Oh. Because I'm configuring my bindings first. So these are the kind of bugs that like you can find in simulation without having a robot. So once you get that robot, like you know it runs. So okay, there we go. Build successful, simulation. I'm going to go into teleoperated. I'm going to turn on my controller again. Look at that. It's autofilling today. This is the best day ever. So in here, we're not going to do anything on the 3D field on this one. We are going to close out all these things. And I'm just going to put volts on one side, position on the other. And I'm going to hit Y. And let's see if it works. Oh, I got to hit play. And so, spoiler, it is not working. And that's okay. Let's go figure out why it's not working. So, did I save this first off? Yep. Joystick y.while true, elevator.set set point, inches out of 50. Let's go into here. Run once, this set point dot replace. Okay. This dot run set point. Cool. And we're going to go into here. Was that Harry? Okay, sorry. Let's look. So something we can do, like update inputs is working correctly. Yep. All right, and here is why I have this code already written, so I can double check my work. So controller voltage, volts out of, calculate position dot in. Oh, that's why. The first parameter is your current height, the second parameter is your set point. I had these swapped. So it thinks it's already in the right position. There we go. Again, errors that you can find in simulation before you get there. Let's go back. Let's see. There we go. And so I'm going to zoom and scroll. And so you can see the volts goes up to 12 and then it comes back down. And the yellow line is your position. It goes up and it thinks it's at 68. Who knows what 68 is? I don't. Oh, it's because it's been converted already. If I get rid of this conversion. Oh, yeah. There we go. So now it's in meters. So Advantage Scope has this cool thing now in 2025 where you edit units. And you can say that this is a length and it's from meters and into inches. And you can see with that p-value, it's settling at 47 inches. It's really hard for you guys to see, so I'm going to say it out loud. I think my set point was 50, so it's about 3 inches too low. That's good enough for this elevator right now, okay? You would go and tune this later. Like, I don't like this bump at the very beginning. That's kind of ugly for your control. You would tune that out. We're not going to do it with the elevator. So this is a line graph of things. Like, that's kind of cool. That will help you make sure it's doing stuff. But what I talked about last year and what I want to talk about more this year is actually seeing it move, okay? And you can do this in 2D and in 3D. I'm going to try to do this in 4 minutes so that we can then take a break, and then we'll get back at whatever. But that's why I have this visualizer class. So I'm going to copy some of this over. The way the simulation visualizer thing works is in these ligaments. And ligaments are literally just lines. You have your panel, which is like the screen you're drawing on. You have the root, which is like your starting position. And then from there, you just draw a line here for one ligament. You draw a line there for another ligament, and there, and there. You can technically like draw a side profile of your entire robot in this and then like make one bit move up and down. So let's define those real quick. Public elevator visualizer. Yeah, so all of this is wrong. That's fine, don't need that. So in the panel, not the root, we want the panel first. This.panel equals new mechanism 2D. And you have to define the size. Technically it's unitless, so I like to, again, add units to everything and just say this. I don't know if I need the in meters part, honestly. That I haven't played with. Where is that import? Again, this is just the only thing I hate. But you define a width and a height of the screen that it's going to draw these things on. So I'm just going to make a 100 inch by 100 inch. Again, it's kind of arbitrary, but it's important for when you're drawing your things. This.root equals new, or equals panel. .get root. We're going to call this elevator. And we're going to put this at 7 inches off, 7 inches in one direction. And what is near doing? Hello. And inches.of, we'll do 7 inches. Oh, that's what it was doing. And yes, I see that error. Just got to set this to an I. Okay, so we've said this is where we're going to start. Then we're going to draw this ligament equals root.append new mechanism ligament 2D. There we go. Going to delete some of these things. And we're going to give it a name again, elevator. We're going to say the length of it. So I'm going to start this by saying this line is 0 inches long. Okay. This elevator is technically at 45 degrees because we were weird. Again, constants are great. The width of the line that you're drawing and the color you want it to be. So I'm going to say color.k green. Sure. And because it got mad, I'm just going to take the one that works, which is all the same exact code, except that line right there. There we go. Put a semicolon. Okay. So now if we run this, you wouldn't see anything. We got to log it, and then we have to update it. So once I finish this bit, guys, we'll take our break. Again, this is basically here. And I'll make this quick because this isn't, oh no, this will be easy. So we just need a method then to update that length. And so we're going to use distance again. And we're going to say elevator.setLength, position.in meters. And we're going to log it to the dashboard again. Then, real quick, in this is the whole reason we wrote this robot state. We're going to just have a private final elevator visualizer equals new elevator visualizer. And every time we update the elevator, we're just going to say elevator visualizer dot update position. Okay, so let's run that. I'm going to go ahead and enable it right away, and then we're going to go into Advantage Scope. There is this mechanism tab, this mechanism style that you can use. So we are going to find the elevator right here, mechanism 2D. And if I did this right, I'm going to press Y, and it goes up, and it goes down, and it goes up, and it goes down. And so you can, what we did in 2023 is we did our elevator. We also attached the arm to this little drawing to make it go up and down and to see those movements. What I'm going to do today is we're going to do those also in 3D. So I'll do that after we take our break, and then we'll jump into the arm. So if you guys need to run to the bathroom, get a drink, or if I'm talking too much and you just want to go check out another session, cool, cool, cool. Thank you guys for being patient. All right. All right, let's kick back into it. So we did this in, when we left off for break here, we had this line going in 2D. We're going to quickly implement this in 3D, and I will give the caveat here that it is not the clearest. The documentation for this is not great, and it was a lot of looking at Mechanical Advantage's code, the writers of Advantage Scope, and reading their little bits of documentation to figure it out. But you can export your CAD files into a certain format. And I actually didn't have them over here, so let me grab one real quick. Where did I put them? Well, basically you make a configuration file. I wish I had moved them over. Here, let me just do a new window real quick and open up like let's see, which one did I do here? If you look closely, I have like 5 versions of this. Is that this one? This one, here we go. Where I've just like redone this a dozen times. There we go. So this, you make a config file. You export your model in like every subsystem that you want to move. So you'll see here I have 4 models. Model whatever is the drive base, model 0 is the elevator, model 1 is the arm, model 2 is the wrist. And you make this config file where you basically say, where is it on the robot? And I basically just spent 2 hours tweaking these numbers until it looked close enough. So it's not, that's the worst part of that. Once you get it, like you can then just use it wherever. But you'll see a couple magic numbers when I do the arm.
How do you convert those files? Because it comes, you have to download that program yet?
Yep, I had to download that program that they talk about in their documentation. I downloaded it. It's some weird open source CAD converter and converted those subsystems. So we're going to use this visualizer again. I'm going to define 2 helper objects here. So I didn't have to do it here because the 2D stuff just handles it with this line. But our elevator is at 45 degrees, which means I can't just say, it doesn't just go up in the air. It goes, when it extends, half of it goes towards the x-axis, half of it goes towards the y-axis. So when we position this in 3D, we have to account for that with some trig. So I'm just going to make a couple helper objects here for the x modifier because we're going to be doing this calculation every single time and it's easier to just not, where we just say what's the cosine of 45 degrees 45, and then this takes radians. Again, you could just define this in radians, but
because the 3D needs
3D needs X, Y, Z, and then like twist, yaw, and whatever the third one is, pitch. So 45 degrees in radians. And every position I'm just going to multiply by that one. Let's copy it. And this is Z, and again, a little bit magic here. It needs to be negative for the model the way I exported it. Unfortunately, it might not be that way for you. A little guess and check on this part. But I have that now, and we already have this update method, so we just need to convert this into a 3D pose. So let's grab the X. That's going to equal position dot times that X modifier that we just made. I'm going to need an elevator Z, which is just going to be that position times the Z modifier. And I'm not going to do a Y because Y is just going to be 0. Pose 3D, not posed. Elevator 3D equals new pose 3D, the X, the Y, which is going to be inches.0. Again, this is one of the places where they did implement the units library into their other classes. So pose 3D can take units. Not everything can. Elevator Z, and then the elevator doesn't twist, yaw, or pitch. I guess technically, no, it doesn't. It's at a funny angle, and we've accounted for that. So we're just going to throw in a new rotation 3D object, which just sets all of those to 0. And I'm going to copy this logger method again and just change this to 3D. We're going to run. And so this is another, like I said, I'm doing everything in the 2025 versions. This is another nice thing that they've changed about Advantage Scope now, is that it crashes. Yeah. When I was doing this as a test run, like the last 20 minutes, Advantage Scope started to drag my computer down. Okay, there we go. So 3D field. I'm going to change this because technically this is our 2023 robot, so I'm going to make it the 2023 field. I'm going to grab pose. So this is the robot. So if you look, and I can see if I can move it here once it shows up. Am I in teleop? I am. Robot, where are you? Let's see if I go back here. There are some bugs with 2025, unfortunately. It seems like where that sometimes this doesn't work. So I'm just going to close this field and open a new one. It is hiding somewhere. Yeah, I mean, is it hiding somewhere? Is that value getting written? Did I grab the right one? Smart dashboard. Is any of the, let's see if anything is updating. If I press Y, oh, had to hit play and fast forward. I do this every time. So when I said Advantage Scope has bugs, sorry Jonah, I have bugs. If he's watching this anytime, it's my fault, not him. Okay, so there's a value. It's somewhere in the world right now, unfortunately. Oh, there it is. So you can right-click this and be like, I want this model to be whatever model. It'll start as the kitbot. I have it here. I forgot to rename it, so it's renamed as whatever Mechanical Advantage names their robot. But then you'll notice right now that if you look real close, actually, like there's stuff just dragging in the front of this model. Those are the different subsystems that we're going to move. So they made it really nice where if I just grab the 3D one and drag it onto here, it makes a mechanism. And now, it was hard to see, but the elevator, this bar right here, showed up. And now, if we did this right, which clearly I did not. Let me double check. Tabs. Let me get a mechanism tab. This is why we have this sim here. And if I take the 2D version of this elevator, okay, so it's working over here. So Yep, something wrong over here. Oh, I never did anything with this. See? Love it. Love it. These are the kind of bugs that you're always going to have. Yeah, it's fine. We're doing it live. And this is what makes this fun. Okay, so now this is like upsetty spaghetti. So I'm just going to get rid of it right here. My robot's back in this corner. So let's enable teleop. We already did. And get him out of there. And we'll zoom back in. Elevator still. Elevator actually is there. Oh, yeah, that makes sense. Now, whee! That elevator goes up and down. And you see Advantage Kit like really being upset at me right now. And so this will be fun the rest of the time here as this kind of bogs things down. But now you can kind of see, and wow, it's really dragging. But I can try to drive around. Woo! It's probably because I'm using OBS and everything all at once here, but it'll do stuff. Okay, so we're going to quit Advantage Scope right now so it just stops killing our computer while we do the rest of this. But we're going to add the arm to that as well so that we can drive around and get positions and see everything as it moves in 3D, which again, like isn't essential, but it helps. So okay, we did the elevator. Let's quickly now do the arm. I'm going to add those 4 files, arm.java, arm.io.java. And so what you'll find here is some fun conversations around software development. As you guys get more skilled in software development, it becomes really tempting to like really utilize the language and start to, you know, make generic classes and make abstract classes that you implement and different things to reuse code, because you're starting to get, as you get a better programmer, you start to become a lazier programmer, and you don't want to do that. And I took a lot of this, or when I was writing this, I was looking at a bunch of different robots and how they were doing their work. And so like one of those was 254, for example. And they have a couple of abstract classes that they use to make some of this simpler. What I'm going to use today, and I suggest you guys just start with, is don't do that right away. Okay, it's really tempting to over-optimize or to pre-optimize, as they say. And while it looks like it will work really well here, the problem becomes as soon as anything about your 2 subsystems diverge, you have to start writing different use cases in your generic. So like the elevator I had in here has 1 motor. If I wanted to add a second motor and log the temperature, the current, the voltage, all of that of the second motor as well as the first motor, now I have a whole different set of things that just doesn't work with my generic, and I have to, maybe now I'm managing 2 I/O objects, and I have motor I/O1 and motor I/O2 and logging all those things. So what I did as an example here, though, and we'll start with the I/O, and actually I'm going to just delete everything here, is Visual Studio Code has this idea called snippets. And it's basically if I type something here, you'll see it's a couple options show up, armsim run volts, etc. I basically took one of the ones I made and made these snippets where if I hit enter here, it starts to autofill some things. And actually I did the wrong one here. I/O, that's what we're in the I/O class. So I/O and I/O2 motor class I made for fun. It makes all of this, and it starts putting your cursor. You might notice I have 2 cursors now. And it's going to fill in that arm. And I just hit tab, and it says, okay, is this an angle or a distance? I say angle. Does that mean you want it degrees or radians? I say degrees. That's angular velocity. And most of that works. Now, it's going to have some issues, if I remember right, because I didn't update this. But if we add all missing imports, and we find that silly... I just put that into my snippet, and that way, if it diverges, if something needs to change, you just change the code. Like you just add, okay, do I need public angle like second motor position or encoder position or something? It still gives you that speed that you might want, but when you're just starting out with your robot project, you don't want to optimize immediately, okay? As you write a couple of these, you might realize that, yep, we have made some decisions where these are going to be the same, and then you can start pulling them so that when you make changes to one, it makes them to both. But when you're starting, I would write them out entirely to start with. Like I said, I was just playing and learning when I did these snippets. But so let's see. I've got position, I've got velocity, I've got applied volts, I've got supply current, I've got torque current. I also have temperature in here. And it added a bunch of methods that we used, or I used initially, that we don't really need. So I'm going to delete the brake mode. I'm going to delete the current. We don't need that. Technically, it made these default values so that you don't have to implement them, but you could. We'll leave that the same. That's just a fun thing with the new, it's probably like 5 or 6 years old now, Java interface. But this I/O class is now done. Great, that was fast. I/O sim, we're going to say this implements ARM I/O. Let's grab all this. And, oh, yep. And so, because I made those default, they aren't going to show up anymore. So I'm just going to grab all of these. Great. And I'm going to add one more that I might have deleted. I'm sorry. Set feed forward, because we're going to do a little bit of control loop tuning here. KS, KG, KV, KA. And I don't expect you guys to know what those are right now. If you do, wonderful. And let's grab that real quick here as well. Okay, so we got all these values. I'm going to delete these implementations. So another snippet I wrote, and again, because you write these snippets by hand, like they have the potential to have bugs, and I think this is where one of those comes in when I was doing a test run of this the other day. And so ARM sim. So this is where now, oh, there's the first bug, get cracking. This is where, now when I said before, like you should probably break these things into constants, because I did this snippet, it makes it a lot quicker to break it into constants. So I want Kraken 60s, I want it to have one motor, the gearing, 75 inches. All right, so now I got to grab these values. Let me see. So these are, again, these are actually the real values from our robot that year. This was 24.719 inches. It was 11 pounds. Its minimum angle, I don't know what it actually was. I'm going to set to 0. Its maximum angle is 360. We're going to start at 0. And there we go. So now I'm going to fix this error, get Kraken, and add all missing imports. Find this import. There we go. Okay, so now you see, now it's a little bit clearer what each of these parameters is, but before I used an elevator sim, this is a single jointed ARM sim. There are, I think, 4 of these sim classes. Elevator, single jointed ARM, DC motor sim, which is just a real basic, motor spins, what's the output value, and then flywheel sim for like shooter wheels. Single jointed ARM sim has this funny estimate moment of inertia, which you just pass in the arm length and the weight in the right units. Okay. So then we've got, let's go to the run volts again. I have ARM sim run volts, which apparently includes the method definition. I'm just going to delete. It's mad that I haven't made an applied volts object yet. And here's the fun thing, like I said it during the break here when someone was talking, but these 2 implementations now are so similar that copy pasting so much of it over. And that's why it gets really enticing to write generics for it. 100% why. And why teams do it. And you can. I'm just saying, when you're starting, like when this is like week 2 of the build season, just write it out to start with. Once you get further, because genericizing things takes more time than writing it, about half the time. Okay, that works. Run set point. We'll do that one next. So we're going to use what's called a profiled PID controller. That means it has a maximum velocity and a maximum acceleration. Again, I just made a snippet here, which adds all these KS, G, V, A, P, ID degrees per second, degrees per second per second. Great. Add all these missing imports, and we want that one, I think. Cool. So now this is a profiled PID controller with an ARM feed-forward class, with a max velocity, a max acceleration. These all get fed into this class through these constants up here. All of that, hooray. And then I can say, again, these snippets, which include the method definition, make my life very easy, very quickly. They can be written during the preseason if you want to do them. And then, yeah, now I have that set point, which takes a current angle, a set point angle, it feeds it into a velocity, feeds it into a controller, and I'm going to double check that it looks right, because I remember during my practice run through, this had an issue, but I also had set the gearing to 4 instead of 75, so it was really struggling to do anything, so that probably was the issue. Set point, set point. Oh, there we go. That's because of this. Perfect. Okay, so now the last things we have are update inputs and set PID, stop, and set FF. So stop is easy. Run volt 0. Set feed forward. So we'll do set PID first. This .controller.set PID. So this will update these values for you. Unfortunately, feed forward does not have that. So this .ff, you have to do equals new arm feed forward and pass those in. And it probably defined it as final, so it's mad. Again, bugs with my snippet that I should just go update, but it is what it is. And so finally, we just need to do the logging part again, which fortunately, like I said before, half of this stuff is identical to the elevator. I'm going to say it's a lot harder when I'm zoomed in like 20 times. It makes it look like I'm doing a lot more movement than I actually am. Again, these are not going to work just right because we don't want position here. We want .get angle, and you see how it says radians instead. So we say radians. These are actually radian and radians are actually the same thing, but it's all the same. Undefined for the type angle. That's why. Needs to be a mutable angle. Get angle, get velocity radians per second. Change this to radians per second. Awesome. And then I think this one included the temperature, which again, for a sim is not going to do anything. But if maybe you're concerned about your motors overheating, an easy thing to just add it here and it gets logged. Basically, once you set it up, anything you add to this inputs object will just get logged. I also have motor connected, which I'm not going to do here, but keep that true. That's what I talked about earlier. Okay, so we now have the sim, we have the I/O, we need the class. I'm going to just go into this class, grab all of it, paste, import this, and then just start changing things. I could just like Control-Shift-F, replace elevator with arm everywhere. But I'm just kind of showing you guys how much gets shared here. I'm not trying to tempt you to write generics with this. I'm trying to tempt you with, once you write one of these, it becomes really easy to write a second and a third and a fourth. And if you do a little bit of practicing before the preseason, once the actual season comes on, you can probably have, once you have an idea of what your robot is going to look like, you can have this set up in simulation like end of week 2. Really easy to do because these are all so similar. This should be an arm instead. This should an hammer. This should be an arm instead. Need to import logger. I think I renamed this one in my snippet, so this should be run set point. No, what's it mad at? Oh, it's because set point's a distance. angle, robot state, and we want arm position. Oh, that's because I probably reused something I shouldn't have reused for a name. I overloaded the robot state object. I need this one. Import command, change this to an angle, and Yahoo. So if I add this to my robot container, again, just copy pasting. I didn't set up an arm Kraken, so I'm just gonna do this. It's mad about this one. And that should all be set up now to view things in the line plot, which is what we will do. So we have about 25 minutes. We're doing great. So I'm going to add a button here. Actually, I'm going to use the Y button again. And so we're going to say that when you hit the Y button, it's going to bring the elevator up all the way, and for whatever reason, we're just going to point to the sky. And we're going to say along with arm.set, setPoint, degrees.of, and we'll just point it straight up into the air. And then, when we go back, we will say along with arm.set, setPoint, degrees.of, and we will point it at like 15 degrees. Okay. So we're at the step now where this should all go into the sim, and it should work if you had PID values. So what I'm going to do now that I didn't do with the elevator is we are going to utilize that logged tunable number that I talked about at the very beginning. And these are a little bit verbose, which is fine normally. It's unfortunate when I'm zoomed in this far, so I apologize. But we are going to make logged tunable numbers for each of these constants. And I'm going to not do it with this. I don't like this. I'm going to say arm gains KP. And the default value is going to be 0. Import. And now let's see if Copilot does it right. Oh, look at that. This is where Copilot really shines. Did it do it right everywhere? PIDSGVA. Look at that. Okay, so we have those now, and we need to just use them. So remember I made that set PID and set feed forward method. The neat thing with this logged tunable number is it has this fun method here, which is logged tunable number dot if changed, and you pass it in a unique ID, which they recommend to just use the hash code of the object, which I'll show you. You pass it in a function that is going to use all the values if anything changed, and then you pass it in all the values you want to see if changed. So hash code, I'm going to delete all this because whatever. The function that utilizes these values, which actually I'm just not going to implement for a second. I don't like the order they did this in. They should have done, but they had to do it like this, I guess, because it's one of those, I forget the name for it, but if you look here, it's one of these, the ellipses ones, which means you can pass in as many values as you want. It's just going to take them all as these numbers. So then if any of these change, it's going to run this method with, and then the values will be updated. So we are going to say io.set PID, kp.get, ki.get, kd.get, and delete that. And we're actually going to take this and also move this up into here so that it's going to pass in the default values right away. Because once we're done tuning, we're going to set these values. And another fun thing with this class is, if I go here, I believe it does some stuff here, which I haven't looked too much, but you can set a value at the top that says if you're in tuning mode or not, so it'll remove a lot of the operations it does if you set this to false. So like when you're actually on the field, it's not grabbing things from network tables anymore, I think is really what it does. And it uses the values you've got. Okay, so I did the PID one. Let's see if GitHub Copilot knows what I want. Nope. Oh. SGVA, SGVA. Look at that. Okay, so now that sets the feed forward. So now, if we run this, see what breaks. Success. Okay, next we'll see what breaks here. My controller turned off. Oh, that's so nice. Advantage scope. So we are going to close this field because it's really bogging down everything. And I'm just going to go to the line graph. And I'm going to look at my code because I bet that still says elevator. Again, copy-paste errors are a problem, 100%, and I can totally empathize with that. Did I enable? Yep. All right, so now we have this arm here. Let's put the position, and actually, I'm going to add a couple things for tuning now. So profile PID controller, remember, makes kind of like an S-curve as it goes up because it doesn't instantaneously try to jump you there. So what I'm going to add real quick to help us with tuning is two more fields to this IO. I'm going to add basically these two fields. I'm going to duplicate, but it's going to be set point position and set point velocity. Basically what the controller wants us to do so we can tune our PID to do that. And so that means I need to update it in the sim, which is right down here. It's somewhere. There it is. And that's easy. We do inputs.setPointPosition. And it's really smart. You do the controller and you can get your set point and it has two values on it. It might have more. It has position, which should be in degrees because we did them in degrees down here. And set point velocity, which degrees per second, which matches here, degrees per second. And so now, enable, I should have these here, set point position. We're going to put that there. That's the set point. So I think, because the way the profiled PID controller works, it has a set point and a goal. And when you do the set point, technically that sets it as the goal, which is where it wants to get in the end. But the set point changes every 20 milliseconds to reach you there. And you'll see this, hopefully, when I press this button. So, edit units. This is an angle from radians to degrees. And so, turns out we don't see it. So so something about what you said is correct, for sure. I was trying to do this without referencing my sample project, but apparently that was an issue. Controller.get setPoint.position. This looks right, this looks right. Here, for good measure, we're just going to take this, and we are going to, oh gosh, replace all of it with the same exact thing. Let's see what happens. So set point, position, controller dot. What are my other options here? So this is also what I'm using up here, which should work. Whoa, duplicated it. See, there's get goal, which is where it should end up, and get set point. So what did I mess up? Yep, calculate is right here, which passes in. So I hover over this. Woo! Calculate takes the measurement and the goal. So it's passing in current angle, and then angle is what's passed in here. All right, so here's what we're going to do. I do have a backup project that I'll look at. Like I said, I've done this like 4 times, and this is the latest one I did. So we're just going to grab this. It's so much nicer to work, but I don't think any of you can read any of that. So much nicer to work there, though. And then let's look at this one again. Set point, this dot controller dot get set point position degrees. So I see something different here. I don't know if it is doing that though. Let's try again. Is it, oh, I know what it is. It's this right here. Max velocity of 0. Max acceleration of 0. Yeah, okay. Again, things to find out. So let's do 90 and 90.
Can't go anywhere if you don't let it.
Nope, apparently 0 just means instantaneous. So all right, here we go. Ready, 3, 2, 1. Whoa, really slowly. So that yellow line is where it wants to be, and that red line is velocity. So you can see it climb and then slow down. Position doesn't change because we haven't set any PID, and then I let go of it and now it goes down. So, feature of Advantage Scope is this little toggle here. Basically makes it so you can start editing some of these values. So inside Smart Dashboard, tunable numbers, ARM, gains, you can see all of them here. So, might be. As long as you utilize, I mean, network tables, you could always do that. Right. This just has a bunch of, this is a little bit nicer. So, we got 10 minutes here. At the very end, I want to just put it in 3D so that I can show you guys. But I want to talk for most of it about the control loop tuning, because that's a big part of being programmers, is getting this right. So you can see I have like 6 values here. Let me fast forward to the end so it keeps up. There we go. I have like 6 values I can tune, 7 values I can tune. We are, for simulation, we're only going to touch like 2 or 3 of them. But I will talk about all of them and kind of the order it makes sense to go in. So this is an arm, which means it has to deal with gravity, right? Gravity will change depending on the angle of your arm, and that's this kg value here. Kg will basically scale based on your arm's angle. Assuming 0 is entirely horizontal, 0 is where you will need the most effort to move it. Up here, you basically don't need kg at all, and it'll take that into account. We're not going to do kg here today because it does not work well in simulation, because there is no, even though there is simulate gravity, like if I don't know, put a 1 here, you can see it's already trying to do stuff. Like blue is now shooting up into the sky. If I try 0.1, it's now coming down because it's not strong enough. So I'm just going to set this to 0. And while I talk, it's going to go back down to 0. KG doesn't make sense for simulation, but it should be the first thing you tune when you're doing a control loop. Basically, creep your voltage up until your arm starts moving, and then move it back down until it stops moving again. Okay, and that's your KG, roughly. KS is called static friction. Okay, and so for things that aren't arms, you use it in arms too, or you can. But for things that are not arms, like an elevator or a turret or even an intake, KS is how much voltage it needs to make it move at all, to overcome the friction in your system. So when I joked about that freshman, like over-tightening things, you might need a higher KS to overcome that friction. Again, it's not a thing we're going to tune in simulation. But you tune those both first. Technically, the way we do arms, KS and KG we set KS to 0 and it all goes into KG. Some teams will do KG where like they find until it starts moving and then how far they have to back off, and then like halfway of that is KG, and then the extra bit is KS. There's a presentation by Team Bread at Citrus Circuits stuff last year that goes into this and talks about that way better than I do. So the first value we're going to tune is the next one. It's called KV, okay? And KV is K velocity. And it's how much voltage per units of velocity. So I'm going to just set a value and we're going to see what happens. Nothing will happen until I hit this button. And so now you can see I have a blue line and I have a yellow line. I'm going to delete the red line. I have a blue line and I have a yellow line. What we want to do is basically, let's increase this some. Let's see what happens when I increase it. There we go. I let go. Okay. So if I zoom in some more, the general idea with KV is that it doesn't matter. You're not trying to get to the position with KV. You're trying to match the slope of the set point here. So you basically want KV to kind of look like a mirrored version of the slope. So I can make this like bigger. And again, it doesn't translate amazing in simulation, but you can see like the slope here is wrong. Like ignoring where it reaches, the slope there is way steeper. So if I go and try to look at what I had before, or what I used for this, let me find it. So it looks like what I ended up with was KV is 1.45. And so you can see they kind of mirror each other in terms of slope. If I zoom in here, it's obviously a dampened version. It actually looks like it could be steeper. Like this looks a little steeper than this. So I would just sit here and tweak this a little bit. And this is why having logging is really important. That almost looks like too much. So I'm just going to average it at 1.5. And we'll call that parallel. That's what you're looking for with KV. Is basically your slope is parallel. It doesn't matter where it starts. It doesn't matter where it ends. It doesn't matter if there's a delay. KV is just matching that. What KA is, which I won't use because it doesn't really work in simulation either, KA is to try to match the acceleration. So it's this little bit right here in the bottom where it's starting to curve. You can tune that to make it so at that point then you almost want it to start at the exact same time as your set point and follow it and basically be a mirror image, but it just might not match, like they might not overlap. Okay? So I'm not going to do KA here. This is going to be the last value we tune then. It's KP. So now we're in, everything before was feed forward. Like if you didn't have an encoder, it would not matter except for logging. It's all feed forward based on your set point. P, I, and D are feedback now. They're based on your error. P is volts per unit of error. I is volts per unit of error over like the last 10 seconds or something, and D is volts per unit of error's velocity. Okay. Generally, we only need KP. So if I like make this like 1, for example, I think that's going to be way too high. Like right off the bat, oh, it's actually pretty close. So right off the bat, it's actually hovering at 14.6 degrees when the goal is 15. If I press Y here, it follows it actually really well. This is simulation, not real world, so it's not going to be that easy. The biggest thing to remember is KP has units. Everything has units. Units is the real, it was the secret title of this presentation, is everything has units. What I actually ended up with apparently was 0.1 in my KP. Let's see. So you notice right away, like it sagged because I don't have a KG to help keep it up and fight gravity. So KP is now sagging by 3.5 degrees. But I press my Y button and it follows it pretty well and does its thing. And then when I let go, it follows it pretty well too. Gravity is obviously doing a little bit of work there at the very end there. But that is, and then I and D, like honestly, avoid I. Just avoid I at all costs. It just doesn't do nice things to you. D, if you're getting a lot of oscillation that you just can't get rid of, D is intended for that. It's intended to smooth oscillation, but you should try to avoid oscillation at all. All right, so we got 5 minutes left. Let's make the arm move in 3D. So we have this arm visualizer. I'm going to copy paste like all the setup here because it's no different than what we did for the elevator. Except I'm going to make this color.k green again. I'm going to find this import. I'm going to grab panel root and arm. Wonderful. I'm going to import logger, the correct one. I'm going to get rid of this because I don't have a key. Okay, so that just again draws the arm in 2D, draws the panel and sets up all of the stuff. We then are going to have a public update method. The difference here, because in 2023 robot our arm was attached to our elevator, we also need to know the height. So I've got angle position right now. I need the height as well, okay, for the 3D stuff. And in fact, really, let's just copy paste this because I will explain it, but delete this. Oh, I need my modifiers.
So did you have to get the height from the elevator?
Yep, so I will have to pass that in. That's why I put all of this in the robot state, because it knows the height and the angle. That way the elevator, or the arm itself, doesn't need to know about the elevator. Again, a little bit of a separation of concerns. So these are all my magic numbers for making that arm sit exactly where it does in real life. I had to move it X 0.07 meters. I had to move it Y 3 inches and Z 0.377 meters. You can tell like I changed units about halfway through here. All of these are probably like 6 inches. This one's probably like 1 inch. And then a weird angle offset here. So now I've got my pose 3D constructed where I find the elevator X and Z, and I add the arm X and Z to that. So the arm modifier is just a constant actually. These are all just constants really, except the height. And then what really changes because the arm rotates is this rotation to 3D. And it really only does pitch apparently, which then I take the position, turn it into radians because that's what this requires. If I go into my robot state real quick and just use this, is it going to do it for me? That'd be really cool. Nope. Do it now. Thank you. And we say in here, arm visualizer.update position and elevator position. We run. And with 2 minutes to spare, we just hope it works out right. We add this tab back for the 3D field. I'm going to get rid of the drawing itself. I'm just going to do axes. I'm going to grab the robot pose. Which should show up. There it is. I'm going to pass the elevator first. Great. And now I have the arm, which I pass, which should actually show something snapping if I make it not a vision target. There we go. So now my arm is in position there. And if I press Y, if I did this right, it goes up and down. And so now, like you can go, and let's see if it freezes. We can drive around and go, woo! And with this now, you can start to figure out, like if this was it, like obviously you can see there's no way to control the game piece. But what you can start working on here now is stringing these things together for things like autonomous, or 2023 was really big on positions of everything. And because we have like a visualization of what the robot looks like on the field, you can get rough estimates of where your elevator and your arm needs to be based on this that you would then tweak when you have it on the real field. But this is a real fun thing. I could then now go into my robot container and start adding a dozen other buttons, and maybe if you really wanted to work with your driver on what feels comfortable for things, you now can start doing all of the fun stuff, the application logic, before your team has finished their robot. All right at 1. Thank you guys. I will be sticking around a little bit if you have questions for whatever thing, but I appreciate you guys being a captive audience. This will be posted, and I will attach the GitHub link for this repo as well, so you can play with it and reference it if you need. So thank you guys.